So that was an example where the iterated integral can go wrong, different each other, of course, for the example of a discontinuous function on that interval. Now, Fubini's theorem, it's stating this part of the video, part 1, will focus on these two iterated integral being the same, not entering this one as a volume double integral. So you look at these two objects and show these two things are the same, under the condition that f has a continuous partial, not the more general condition that f is continuous. So that we have tools in calculus series that we can prove this one, right? So let me start with the fundamental theorem of calculus. All right, it's the important part. In our courses, we usually introduce this version first. Don't think about existence of antiderivative, just assume it exists. Then we can show, fairly simple, and using mean value theorem again, that and knowing this integral exists, it should be the difference of these values of antiderivative like this. So that's a pretty neat proof itself. But the second version, the more detailed version of the fundamental theorem of calculus, actually handles the existence of the antiderivative. So for that, it's more complete and more correct in mathematics in many ways. So for that, we define this one because ft is continuous. This integral always exists no matter what the x is, and relative to a is fixed. So what we are varying is this upper limit and create a function out of it. And this calls area function. So again, this is fixed, and what we are changing is upper limit. So here's a situation, and this usually represent the signed area. Here, as x varies, you can see this shaded region changes, therefore area changes. So we can look at this as a function of x. As x varies, there's number associated to it, namely the area. And using all those integral techniques and stuff, and we show the derivative of this function here is actually f of x, the integrand function replaced with x in the variable. So this is the full version of fundamental theorem of calculus. Of course, using this version, we can show that. So just like what happened to the one variable case, we do a similar thing. Our interval is not just one thing, one interval. It's just our domain here is actually rectangles. So we have things like this. And we're talking about this double integral, and it seems like it's reasonable to consider something like this, just like the fundamental theorem of calculus. Let me explain what this is. A and B as left this corner is wrong. It's supposed to be C. I'm sorry about the typo. This part is supposed to be C. A and C is the lower corner, and x and y is right limit and upper limit for this region inside this rectangle there. So the volume over this smaller region is what this one is calculating. Okay, so we can make a function out of it. X varies freely and y varies as another free independent variable. So this is two variable function. Next part is often neglected by students. When we write it like this, it's worth thinking about the existence of this function, or the continuity of this function. So toward to that, we have to understand this is well defined and stuff like that. Okay, that's also fun. So here's lemma 1. Let's see what that says. It's lemma 1. If g of xy, it's just a general statement, has continuous partials. G is not any of this, just any continuous partial function with continuous partials. It says this limit is equal to that. Let's think about this one. This one is integrating with respect to y, and there is x in there. Therefore, we should assume x is fixed relative to y, and we're integrating with respect to y. Just like iterated integral there, we have this notion. And after we do that, and we have this quantity depending on x, if your x is getting closer and closer to x0, what's going to happen to this quantity is actually the same as you just plug in this x with x0. And that property is guaranteed by this property that g has a continuous partials. It seems like one of those things in the calculus that this limit is basically plugged in here. What's the big deal about it? and kind of stuff. And it is a two different notion. Especially here, let me phrase it this way. This is actually a different order of operation. Let me say it this way. We do the integral first, and then do the limit. Or do the limit first. You plug in x equal to x0 because g has continuous partial. Particularly is a continuous function. So if x approaches x0, this function value inside must be gx0y. But applying this one there like that is a different order of operation. So we're doing this limit inside first, then doing the integral later. So this statement is basically saying order of operation of the integral and the limit doesn't matter as long as we have this property. Whenever you're talking about order of operation doesn't matter, you can safely assume that is usually non-trivial. And often when it gets things complicated like this and we ignore that and think, hey, doesn't matter, but it actually does. And we have to carefully analyze this order of operation and explain why it doesn't matter. So I use this following example. So I wrote it up here as an, let's see, and I summarized it here, sorry about that. So here's an example, right? We're going to show this h approaches are inside depend on s and h, and we're going to calculate this one with some specific example, and then we're going to send h to 0. Then we're going to send h to 0 first inside, and then we're going to calculate the integral. See if that's sometimes different. Of course, if g is continuous, this is going to be always the same, so this example must be something g and this is discontinuous. So I wrote it up there. So this is example. H times s raised to h minus 1. Because this is exponential, when s equals 0, it's going to be a problem, right? So when s equals 0, we just simply define it as 0. When s is not 0, this is always well defined. But we had to assume s is positive. I forgot to wrote it here because it's exponential. As a function of real value, it has to be s being positive. So it's better to write s greater than 0 here. So let's look at this part, and we're calculating this integral first. So there's this integral right there, 0 to 1 gsh. When s is not equal to 0, we're doing this integral first. When s is not equal to 0, it follows this expression. But when s equals 0 right there, and it's going to be 0, so we can treat this one as improper integral, or if you look at the Riemann sum, there's no problem with this definition. Actually, if you use the Riemann sum, this function is well defined. I mean, this integral is well defined. I'm pretty sure this is probably not continuous, especially because of this s equals 0 is artificially defined here. You can probably find a weird path that it behaves wrong. This is discontinuous two-variable function, or one variable function for s given h. Yeah, and let me say that again. I was just mumbling to myself as usual. When h is very small, then is 1 minus h minus 1 is a negative number, so it's going to basically look at 1 over s something, s to the power, so it's reciprocal. So at s equals 0, this function will be undefined, goes on. So we have to look at this as an improper integral. So let's proceed, and knowing that the 0 is kind of quantity close to 0, h is constant, and antiderivative s to the h minus 1 is 1 over h times s to the h. And this nicely h cancels. That's how this one was made and cooked up. So this s to the h is, if you plug in s equals 1, and 0 to the h is some number close to 0, not necessarily 0, so this makes sense. And if this base here approaches 0, that's going to be exactly 1 for a given h is not approaching 0 yet. So that's why this makes sense. Then after that, if you let this h approach 0, then this whole thing will be like this. Limit h approaches 0, this inside was calculated as 1. It's not depending on h, therefore limit is simply just 1. Let's do the other operation. We're going to do this limit h approaches 0 in there first. So here's the definition. Okay, given s, if s equals 0, it's always 0, so therefore it's going to be 0 no matter what happens to h. If s is non-zero, so there is this s equals 0 there, non-zero number, and because s is not changing no matter what this happened to the exponent, because h approaches 0, this whole thing must be 0. So if you let h approach 0 inside first, that's just flat out 0, so integrating 0 function is going to be 0, like this. So what happened here is h approaches 0 for fixed s value. This whole thing approaches 0 inside. But if s is kind of close to 0, for given s value, this whole thing approaches 0 as h approaches 0. But that given s value, if the given s value is close to 0, then this whole thing approaches 0 a lot slower. Start from all the way up there, some large number, come down to 0, it takes a lot more time. So that kind of affects this this integral right there. So if you don't do that h approaches 0 first, what happened around that 0 thing is kind of picks up some significant number, just like that x minus y divided by x plus y cubed example we did. Kind of similar. So the point here is that order of operation doing the limit and integral matters. And if it doesn't matter, you have to, in your argument, if you want to say it doesn't matter, you have to use in your argument that the property of the g being continuous or something. Otherwise, your argument is probably wrong, because here's an example. So since this is the important part, we have to look at the proof carefully. This is the where make things happen, the order of operation. Right? So we looked at example. Let's see why this is true under this condition. Continuous partials. Okay. Beginning, and just like the earlier videos like Clairaut's theorem and differentiability, it's about handling this operation limit carefully. So all of those things, what we did is remove this limit and then look at this object to object and show they're actually equal to each other. So here's this left-hand side without limit, and here's the right-hand side. I put it together and I subtracted it. I want to investigate how different is these two values as x approaches x0. And there is no x here, so this is a fixed number. All right, this is actually absolute constant, and this is a function of x. Well, since we have a same limit for this dy integral, so we can bring it inside. And we're looking at, let's see, y and y is the same, and x0, that's the different part. So we can look at this as a function of x, y didn't change, a function of x, and apply, you know what, the mean value theorem. That's why this continuous partial is going to play, how this continuous partial is going to play in. So when you apply the mean value theorem, we're looking at this function as a function of x, and y is fixed here. So mean value theorem says the difference of these two function values is going to be the same as the value of a derivative at some special point times the difference of the input, x and x0, x minus x0 multiplied to this special value of the derivative at x. Therefore, it must be the partial. And the special value x star, its existence is argued, but we don't usually know how to describe it better than just this, in between, the value in between x and x0. Alright? So that's mean value theorem again. From here, we're going to use the fact that x minus x0 is causing, the whole thing go to 0. Then we can kind of factor this out, because it doesn't have y in it at all. And this one is not causing any problem. The reason this is not causing any problem is this condition of a continuous partial. Okay? So here's how. These are integrals. Integrals are usually the sum of the stuff. So when you sum up, if you change these sum n to a positive, and you get necessarily bigger, there's no cancellation. So that's why inequality works like this. If you put inequality, you can change everything inside to the positive by putting absolute value. you make the integral bigger. So again, x minus x0 doesn't have y in it. It goes outside, and inside, change to a positive value, then integral is going to be necessarily bigger than or equal to. So I wrote it up there. So the thing that we're interested in here is smaller than this estimate. So here's where the continuity of this partial kick in. The gx is a partial derivative, and which is assumed to be continuous. And what happened to this x star is x star is just around x0. This x is usually very close to x0. So this x star is safely in this tiny bound region around x0. But y here is varying very big from c to d. But in all that, what is happening to these two variables is they're all in here. X star is somewhere in here, and x here, and y is somewhere there. So there's a safe, tall rectangle in xy plane, so everything is taking place in there. Because gx is assumed to be continuous by something called extreme value theorem, that's another topological flavor in it, so we don't prove it here, but we've seen this statement, extreme value theorem, in your calculus course. For continuous function, there must be maximum on this plate. That maximum is going to be denoted by capital M. So if I replace this function value, that is depending on your x star and y, there's constantly changing when you do this integral, but they're all less than this one fixed value M, which depends on x0 and only the function itself. So M is constant here relative to y, and make it a lot bigger. But that's still enough to conclude what we want. So here it is. M is constant, that is pulled out, and what's left here is in invisible 1. Then c and d, dy gives you this d minus c. That's an integral. So all this thing is what this right-hand side is. So this quantity is sandwiched in between this estimate. This m is fixed, d minus c doesn't change. Only thing it changes as x approaches x0 is this part here. That guy approaches 0. Finally, by squares theorem, this one must approach 0, and that's this result. This quantity right there approaches that quantity as x approaches x0. So, to sum up, the continuity of the partial gives you an absolute upper bound for the partial derivative that estimates nicely of this difference of this true value under the mean value theorem, using the mean value theorem. So that's how this condition kicked in and make this happen. So let me say one more thing before we move on to the next part, is this lemma and this part where we make this transition from here to there. If we have an even better condition than continuous partial, if we have just the continuity, and this, there will be some m that does this job, like we saw that at the end. I think it's called equicontinuity conditions, that it's done on this closed interval over continuous functions on this closed interval, and there will be this nice equicontinuity condition that guarantees that we don't have to, guarantees the maximum, and that doesn't depend on other variables that is involved here. So this is the part where we're using this continuous partial condition, and it can be actually done using just the continuity. Alright, so let's move on to the next part. So here, this is where we digressed a little bit, because we defined this iterated integral function, and I just want to make sure that this is well-defined function. For example, inside it here is integral with respect to t, so s is kind of given. So given s value, there is t integral, therefore this integral value will vary as s varies. What we have shown earlier is that this function of s is going to be a continuous function. I should have included an extra statement there, but if you go back to the lemma 1 and see that again, it's exactly what it says here, is that as s approaches s0, this integral value will be the integral at s0. So that's exactly the continuity condition on this inside integral part as a function of s. So the inside function is continuous function. So outside integral have this continuous function inside, therefore it's integrable. So this function exists. So those who don't think about the existence too much, that seems like something that unnecessary thing is done. But if you think about it, if it's quite a serious business there. Before you do anything about this one, you need to know this actually makes sense, and we looked at the detail of that statement. So here's actually what we're doing here. We fix inside s value and then do the integral t. Then we do integral with respect to s. We've done something like this, like a partial derivative. We fix s there and differentiate with respect to t, and so on. So this something called iterated integral is somewhat like a partial integration. Nobody uses this term. I just made it up to make a connection to how we do the partial derivatives. But this order of partial derivative is called Clairaut's theorem, right? And here we're talking about order of partial integration, and then I guess we should call that one as a Fubini's theorem. So there's some connection between Clairaut's theorem and Fubini's theorem. So I wrote here that reminds us of Clairaut's theorem, and actually the connection is very nice, so I'm going to do that to motivate next part. So here it is. This function we have defined as an iterated integral. It's well defined, and if you integrate with respect to x first, then you look at a function here, this entire inside here is a function of s, right? So if you differentiate with respect to s, this whole thing is a function of s, and with respect to s there, then it's really just fundamental theorem of calculus, because we have one integral, whole inside thing is treated as a function of s, which is continuous. Then by fundamental theorem of calculus, that inside function with s replaced by x, that was the fundamental theorem of calculus. You can pause the video and go back to where the fundamental theorem of calculus was introduced, but that's exactly what it is. So if you differentiate one more time, if you first integrated x, then in subscript notation it goes inside, and outside, if you do one more time y, again the fundamental theorem of calculus, this function here is the continuous function in t, so therefore if you integrate it, if you differentiate this part by theorem, is f of xy. Let's do the other way around. That's the Clairaut's theorem. Differentiate xy, and we're going to do yx, so y first. Then here's a problem, that outside integral is about the function variable x, so we're integrating with respect to s, and this integral with respect to y will affect the inside part here. So let me address it this way. If you think about the definition of derivative, it involves limits. So basically this one is kind of in its nature is a limit operation, and then there's an integral, and we want this one to affect this integral inside so that they cancel out, but there is this integral in between. Remember, there's lemma 1. This whole deal about the lemma 1 is that passing this passing this integral is not that simple. So that's their examples given, and whole proof was to justify this process. So you have to be careful in that one. But if it is just a simply limit, and if this is an integral, and if we know this is continuously this function is a continuous partial, and then you can pass it quickly. But since it's not, it's the limit, and we're gonna justify this process as well carefully. But at this point, we need a theorem to get that limit go inside and kind of cancel that y integral right there. So we need a theorem. There are two ways to go about it, and the first one is interesting, so I wrote it up here, is actually Fubini's theorem. Remember, we're not yet trying to prove any Fubini's theorem. What we're doing here is that we have this iterated integral function defined, which it picks up a volume. Then we're just integrating 2 times to see if this one satisfies Clairaut's theorem. So let's use Fubini's theorem to show this one actually satisfies the Clairaut's theorem. All right? The conditions in the Clairaut's theorem is having the continuous partial xy and yx. But We're not examining any of those. We're just looking at this derivative there. Now, Fubini's theorem allows us to swap this to integral. So ds goes inside and dt. If you think about what we did for the partial derivative of x first, this derivative operator and then y integral here cancel. That's the fundamental theorem of calculus. So that swapping allows us to, not passing integral, just right next to each other. So they cancel and it becomes like this. Now if you differentiate with respect to x, that becomes f of xy. So conclusion is this iterated integral function here, we define it like this, is going to satisfy Clairaut's theorem when we used Fubini's theorem. But it turns out, try to use the Fubini's theorem, establishing this Clairaut's theorem is useful. So next, that's our outline. So we're going to prove this Clairaut's theorem, not using Fubini's theorem, and then prove Fubini's theorem using this Clairaut's theorem result. Interesting. So here's our target, the iterated integral function, and differentiate with respect to y. Let's repeat it like this. Let's look at the definition. Not the definition, I should have re-examined the slides first, and then I'm setting out the plans again here. F of xy, and this part was easy because the way it's defined is in that order. Now we're going to show fyx, which is the other way of a derivative. We're going to show this is exactly little f of xy, not using Fubini. So this part is something I didn't say, so here's this. All right. So let me show you how this one, establishing this fact here, is going to help us to prove the Fubini's theorem. So this is not the proof of this box result. What comes here is the proof of Fubini's theorem using this result right there. So let's look at it here. This a, b, c, d, the usual integral in the Fubini's theorem. Then we write inside using this fxy in there. That's the function, fxy, if we establish these two things. Then inside integral is with respect to y, but that's exactly the last differential operator done to their capital F. So these two not cancel this antiderivative with respect to y. So we have this antiderivative with respect to y of this f of fxy will be fx, because that's y is in that position. So that's fx, and we're plugging in y value in there, and d and c and d here. So that's the evaluation theorem of one variable function. Now inside here is fx, and there's a dx operator there. The antiderivative of this one with respect to x will be just f. So I put up here, this one has fxd, that one has antiderivative fxc, and then plug it in b and a. So b goes in there, bd, that's what you're seeing there, and b is plugged in here, and then bc, that's what you're seeing down there, and a goes in there, ad, that's negative ad, and a goes in there, but it's negative and ac. I think I did this ba to this term first, then minus ba to this term first, then later. And that's how I usually do it, so that's what I did. Okay, these are the terms, bd and ad and bc and ac together. And there's this negative sign. So I wrote it up here. That was a conclusion. If I do a, b, and c, d first, it turns out these are the four term values at the end. Now let's look at this one, CD and AB. We're trying to show these two are equal to each other. So now inside the dx integral, so if I use this version right there, you can find the antiderivative easily. So that's why I wrote this one. But fxy is the same by Clairaut's theorem we are supposed to establish here. So right there is fyx, and x and the dx cancel. Not cancel, it's an antiderivative, simply just fy. So here's fy antiderivative evaluated at a and b. So b plug it in there and a plug it in there. So it's integral dy, so fy and fy, clearly the antiderivative is plain f. So if you plug it in here, that antiderivative is fby, that one antiderivative is fay, and D and C is evaluated. So let's do this one correct way this time. D and C evaluated here. The D plugged in there, D, and C plugged in there, that's C. Negative changes the sign, so D plugged in there is AD, C plugged in there, positive AC. Now if you compare these four terms here, they're exactly equal and in slightly different order. So we prove that these two things are equal to each other. So that's Fubini's theorem, which relies on this result, which seems like a Clairaut's theorem. Clairaut's theorem requires the continuous partial of fxy and fyx. Establishing that fact is as much as work of this one here, so we rather just show this one. It's simply that. I mean, the first compute fy first, then it's going to be easy to compute fyx. So we're going to just focus on this part right there. So here, that's the thing to prove now. So let's begin by computing fy. So definition of fy, alright? Definition involves limit h approaches 0 of this quotient difference. So we're doing fy, so that's why the y slot, y plus h and y, and x is fixed. Now, like we did in earlier videos, like in all the other things, limit is causing a problem, so get rid of the limit and handle the quantity without the limit symbol in a different way. So that's how it goes. So q is going to be the quantity of this whole thing without limit. So 1 over h, that's this part. I'm writing out the definition of f of xy. So f of xy is this iterated integral function. X goes up there, y plus h goes up there, x goes there, and y goes there. And that's exactly the definition of capital F of xy. Okay. So this a and x and this a and x is the same. So we can bring this inside together. So this ds goes outside. Inside is a 2 integral. Right? Again, this outside integral is the same limit, so we can bring it inside. If you just look at the inside part here, you've done this some in your Calc 1 probably. Going from y to y plus h, and going to c to y plus h, going from c to y, and subtracting it is the same as going from y to y plus h. Sorry, I realized that I decided to approach in a different way. That's easier for you to see and recognize how the mean value theorem kicks in. So I decided to call this as a function like this, and gsy. So that's going to be this function where c is a constant, and then this part is the function part, and s is a kind of parameter, some given number. So this whole thing is a function of s and y then. So that whole part is going to call this gsy plus h. And that part is going to be simply gsy, and this one is gsy plus h. So here's where we're going to use mean value theorem first. We do fundamental theorem calculus later. So let's write it. This one is a gsy plus h, and that one is gsy. And 1 over h is constant. There's another depending on x or s or t, anything. So it can go inside like that. So this is mean value theorem. Two function values and divided by the difference of input right there. So it's derivative, value of the derivative, times this difference, which is h that cancels with that. So mean value theorem gives this is exactly equal to special value of the derivative. All right? Here's we're looking at g as one variable function. I'm using this prime notation. Special value somewhere in between y and yh, y plus h. There's y star, depends on h and all the other parameters involved in here, but it's simple as this. So I summarize it up here, all of them. This whole thing is now q, that's where it started. Summarize it as an integral of special values of the derivative. Now here's where you use fundamental theorem of calculus. If you look at the gsy, right, differentiating this one, because this main variable of this function gsy is y, differentiating this one with respect to y in here, that's exactly the setting of a fundamental theorem of calculus. So this is going to be just fy if you differentiate it with respect to y. I misspoke, it says fsy, there's no partial, it just cancel this integral. So that inside is just simply fsy in there, but input of y star, so we have to put the y star in there. Okay, so again, here is where it's taking place. The mean value theorem kind of overcomes the interaction, the order of operation between the limit and h, and we'll put it all in here. Next part is also very crucial before I state it. This y star depends on lots of things, but as h approaches 0, it's for sure that y star approaches y, right there, that number, because y star is in between y and y plus h. But it depends on s, because the whole setting depends on s. So that's, and its next part is, therefore is important. We're not going to differentiate. The key part is we're not going to differentiate with respect to x first. We're going to send at this stage h approaches 0. But that was a lemma 1 again, this integral with something inside there, and limit is outside, limit h approaches 0 can go inside the limit h approaches 0 in there, right? So we kind of rewrite these derivative definition into a limit situation nicely like this, so that we can use the lemma 1 again. We have established already. So limit h approaches 0, that becomes almost y, and that lemma allows us just to replace this one y. Okay? So this fyxy is limit h approaches 0, this quantity is really indeed this one. That's, if you think about it, that's what we wanted to prove. The limit actually goes inside the integral and became cancelled. The differential operator canceled with the inner integral dt, which is what just happened. And we proved it using the definition and the lemma 1 and mean value theorem. And also because lemma 1 required the continuous partial property, so we use that too. So I forgot to show this part, so we use this lemma 1 here. So we're almost done, so let me summarize it here. If you differentiate with respect to y, and the dy is outside, integral y is inside, there was a problem, and that's what we just proved. We looked at the definition, and that limit passes in there, nicely cancel with this one, fundamental theorem calculus across another integral. So we have shown that this thing is the integral. I kind of did not organize this one nicely. Let me show you. And here, this is supposed to be fy, right? This is fy. So if you differentiate with this x again, that's going to cancel. So that gives you fxy. So that's this part here proves the fyx being fxy. So that's fxy being fyx being fxy here. That's, we have proved it earlier. And this one is, I'm showing you, there's something we did earlier again. So what happens from now is that we actually finished it already. Once we have this Clairaut's theorem result proven, then we've shown before these iterated integral, and inside fxy can be organized in two different forms, fyx and fxy, and be able to go through the antiderivative easily by playing with this different order of derivatives. And at the end, these two things turns out the same. All right, this is the one that uses continuous partials. In part 2, what we're going to do is that we look at this Fubini's theorem again, but we focused on these two parts, this iterated integral. How can you show an iterated integral equal to each other? But in part 2, we're going to go back to this original setting. The double integral is the motivation of doing this iterated integral. So assuming that this double integral exists, and we're going to show why is these two things equal to each other. Once you establish this section, cross-section volume is equal to double integral volume, then this is just automatic. Just our usual intuition says. But if you ask yourself about what the definition of the volume is, then it becomes non-trivial. See you at the part 2.